In the video for 2012 Part A, we sort of built up this flowchart where we start with an acetal, we go through the hemiacetal, and we get to the ketone. And we saw how each of these curved arrow patterns changes when you go in that reverse order, when you're hydrolyzing the acetal, when you're using water to break it apart and turn it back into the ketone. So let's just come up with what those molecules are concretely in this example, and then we'll go step by step and fill this flowchart out, draw the mechanism for the hydrolysis of this. They give us the acetal. So the acetal is this cyclobutane ring with two methoxy branches. So those are your two ethers that are attached to the same carbon, making that an acetal. So your two ethers, one here, one there, attached to the same carbon. Now, in a hemiacetal, we'll still have one of those on, but one of them will come off. And so we'll have that cyclobutane ring. We'll still have one of those methoxy groups on there, but the other one will come off and it will be replaced by an OH, which is coming from water. Ultimately, that OH is destined to turn in to the ketone. So for the ketone, we continue to have that cyclobutane ring, but the carbon that was the acetal, the carbon that had the two methoxy groups on it, turns in to a carbonyl. And ultimately that carbon, as we said, comes from the oxygen there comes from the OH in the hemiacetal, which comes from water. So these are our landmarks as we go through this mechanism. These are the features that we'll want to make sure we run into, and I've ordered these steps. I've ordered those on the left here so that you can follow along. I would encourage you to write those out and to write the mechanism underneath them so that you never lose your direction. You never forget where you are or where you're going. So here we start with our acetal. And I'm going to draw the methyl groups. I know they write them as Me. I'm going to write the CH3s in there. So this is really the same thing as this molecule up here. Well, the first step is a proton transfer, and that's because we want both of these molecules to leave, and right now they're bad leaving groups. If they left, you'd have an oxygen with a full negative charge, which is something that is unstable. So they're bad leaving groups right now. We want them to leave, so we have to turn them into good leaving groups, and that's why we have some catalytic acid here. They've given us hydronium, so we can use that hydronium to protonate, to add an H+ to one of those oxygens. So the oxygen here has a full positive charge. Each of those hydrogens has a slightly positive charge. They're losing their electron density to the voracious oxygen. And so these oxygens in these ethers will bump into that molecule. The slightly negative oxygen will steal the slightly positive hydrogen, and the electrons will snap back onto the oxygen of the hydronium. So that's our proton transfer. Now we'll end up with basically the same molecule, it's just it will have an extra hydrogen attached to it. So instead of a lone pair here, you would have a hydrogen, and that'll have a full positive charge because the oxygen is bonded to three different things. Notice that the hydronium also turns into a water. It loses its H+, and so now it's just water. Well, we now have an awesome leaving group. If that left, that would be methanol, which would be very stable. It just needs a small push, and the push comes from the neighboring ether. The carbon here is slightly positive because it's losing electron density to both of those oxygens, and the oxygen is slightly negative. So these electrons have been eyeballing that slightly positive carbon this whole time. Now when they swoop in and try to form a bond there, because we have a good leaving group, it kicks the other group off. And so there is our loss of a leaving group. The molecule we have now will have a double bond to the oxygen here with the methyl group on it. Notice that oxygen will have a full positive charge because it has 3 bonds. And then we have a methanol molecule. Methanol molecule that popped off. So we've removed one methanol molecule. And we've made an amazing electrophile. This carbon here, the carbonyl carbon, is slightly positive because it's bonded to oxygen twice, but now the oxygen has like a superpower. It has that full positive charge that, combined with its electronegativity, allows it to really steal electron density from the stuff nearby. And so especially this carbonyl carbon. So that's very vulnerable. And we want a nucleophile to come in. Now, the reason we want the nucleophile to come in is because we need this OH here. We're adding something on in this process. We're adding an OH on. Now you can't add OH minus as your nucleophile because we're doing this in an acidic solution. The OH minus would instantly be neutralized. It would turn into water. So water is the nucleophile that you can use. And we formed water in the last step. So we could have water here. And the slightly negative oxygen on water acts as a nucleophile and attacks the carbonyl carbon. That breaks the pi bond. The electrons go to the oxygen to help stabilize its positive charge. And that gives us this molecule here. The oxygen now is just bonded once. It has 2 lone pairs, so it's neutral. And we have a water molecule sticking to that carbon. Now the oxygen in the water molecule has a positive charge because it has 3 bonds. So we're almost at the hemiacetal. We just need to stabilize this, and we can stabilize it by doing a proton transfer. We can take another water molecule and the slightly negative oxygen sticks to and steals the slightly positive hydrogen. The electrons that we're attaching it go to the positive oxygen to help stabilize that. That's a proton transfer. We're transferring that hydrogen, that proton, from one molecule to the other. And when we're done with that, we end up with our hemiacetal. So we have both the methoxy group, the ether, and an OH, an alcohol, bonded to the same carbon. So ether, alcohol, and the same carbon, that's a hemiacetal. Okay, well, we want to get rid of this second methoxy group. We want to just have a double bond to this oxygen. So we want it to leave. But as we saw before, it's a bad leaving group right now. If it tried to leave right now, it would have a full negative charge on an oxygen, which is unstable. So we can treat it with acid and put a hydrogen on it, an H+, and that will take care of its charge. So the slightly negative oxygen in this ether will attack one of the slightly positive hydrogens in the acid. It'll attack the hydrogen, the electrons snap back toward the positive charge on the oxygen. So that is our proton transfer there. Notice we're transferring this proton from one molecule to another. And so that gives us basically the same molecules we had before, but with another hydrogen on it. So instead of those lone pairs, you'd have a hydrogen there. Now that oxygen will have a full positive charge because it has 3 bonds. Well, now that's an awesome leaving group. And so all it needs is the smallest nudge, and it will pop off the molecule. The carbon between the oxygens, it's losing its electron density to both of them, and so it's attracting the oxygen next door. So that's always been trying to form a bond there, but now when it goes to form the pi bond, it kicks the leaving group off because it's a good leaving group. And so you get loss of a leaving group. Now that's going to leave us with this molecule. And we also have a methanol that has left. All right, well, this should remind you a little bit of a molecule that we've seen before in this reaction. That should tell you, oh, that's an amazing electrophile, because we've kind of seen it before here, something very similar. Basically the same thing, but instead of a methyl group, below we have a hydrogen. And we saw how that turns this carbonyl carbon into an amazing electrophile so that even a weak nucleophile like water could attack it. But here, we actually don't want a nucleophilic attack. We want a proton transfer because we almost have our ketone, which is our goal. So we can take a water molecule and just take off that hydrogen there. So the slightly negative oxygen is sticking to that slightly positive hydrogen. When they bump into each other, it sticks like Velcro. The electrons go onto that oxygen, and that's that proton transfer that gives you the ketone. So, overall, we did the reverse of acetal formation. We did hydrolysis of an acetal. We turned the first ether into a good leaving group by doing a proton transfer. Then we pushed that ether off, or we pushed that off as an alcohol. That's loss of leaving group. That created an amazing electrophile that a water molecule then attacked, in nucleophilic attack. The water molecule needed to be stabilized because it had a positive charge, so we did a proton transfer. Then we just had to kick the other ether off. It's a bad leaving group. We turned it into a good leaving group by doing a proton transfer. Once it was a good leaving group, it had to leave, so we did loss of leaving group. And finally, a water molecule came in to help stabilize the OH that was left through a proton transfer, and that gave us our ketone. All right, we'll follow the same process, the same method of thinking in this next one, C. So first, let's draw the molecules that we have in this sort of flowchart. They give us the acetal. So the acetal is the exact molecule that they give us. The hemiacetal will have one of those oxygens taken off. So you'll still have one of the oxygens on there, and you'll have 1, 2, 3 carbons, but then you'll have the other one taken off. So notice, the two oxygens are attaching here. So that's the carbon that's going to lose the ethers, because that's where they both attach. And so the ethers are connected by a carbon chain that has 3 carbons in it. So 1, 2, 3. One stays on, and the other one becomes an OH. Okay, in the hemiacetal, you don't just have one of those go off, you also have an OH go on. Now, in the acetal, we're removing one of those OHs, and we're introducing, we're removing one of the ethers, and we're introducing this OH. Ultimately, that OH is going to be the ketone, oxygen, the carbonyl oxygen in the ketone. So for the full ketone, we remove both of the alcohols. We only have that little string of a carbon chain on top. Okay, so that's the overall process. Let's think about this one step at a time. First, we have this sort of upside down ketone. Now we want these we want these ethers off of the molecule. But right now they're terrible leaving groups. If they tried to leave, they'd have a full negative charge, which is not stable. So to make them a better leaving group, we're going to use the acid that they give us in the exercise. So we'll have this hydronium. And the slightly negative oxygen in the ether will be attracted to one of the slightly positive hydrogens in the hydronium. So the ether oxygen will stick to that, it'll pull the electron, rip it off, and the electrons that were keeping it on the molecule will snap back onto the oxygen to help stabilize its positive charge. So that's proton transfer. We're transferring this hydrogen, or the proton, H+. So what we get with that is almost the same exact molecule, except now, instead of a lone pair, that's going to be a bond to a hydrogen. Because of that, this oxygen has 3 bonds, and so it has a positive charge. And now, because of that positive charge, it's a good leaving group. The carbon in between the two oxygens has a slightly positive charge because it's losing its electron density to them. So, the oxygen next door, which is slightly negative, is really tempted to try to form a new bond to that positive position. And now that this other molecule is a good leaving group, when it tries to do that, it kicks that other molecule off, so that we have loss of a leaving group. When that leaves, we end up with the oxygen here now having a double bond to the carbon. The carbon has the 2 carbons there. This oxygen will still have these, but the oxygen on the other side is just an OH. So that's the sort of strange-looking molecule that we formed. Now this oxygen on the left has 3 bonds, so it has a full positive charge. And what you'll see here is that we have a really good electrophile. This carbon here is a really good electrophile because it's double bonded to an oxygen, so it's really losing electron density that way, and the oxygen has a full positive charge, so it can really tear the electron density away from that carbonyl carbon. So the carbonyl carbon here is very slightly positive. It doesn't take a lot for a nucleophile to come in and attack it. Now, we want to get an OH on the molecule. We can't use OH minus because we're doing this in acidic solution. So instead, we're going to use water. Water can come in. The oxygen can act as a weak nucleophile, slightly negative. It can come in, attack the carbonyl carbon. That'll push the pi electrons onto the oxygen to help stabilize the positive charge there, and that's our nucleophilic attack. Now what we'll get is we'll have those 2 carbons sort of going up. We'll have a water now attaching. This oxygen has 3 bonds, so it'll have a full positive charge. On the other side, we have this oxygen, now has 2 lone pairs, so no positive charge. This has 1, 2, 3 carbons, and then the OH. All right, well, we're almost at our hemiacetal. We have this carbon here that's bonded to an ether on one side and almost an alcohol on the other. We just have to stabilize this positive charge. And we can do that by doing a proton transfer. We could take water, the slightly negative oxygen on the water can steal the slightly positive hydrogen here and have those electrons snap back onto the oxygen. So that's our proton transfer. And what we get after that proton transfer is this molecule here, which is a hemiacetal. The carbon here is bonded to an ether on one side and an alcohol on the other, so it's a hemiacetal. Okay, well, we just need this other ether to leave. It's not a good leaving group right now, so we need to make it a better one, and we can use the acid that we formed in the previous step. We can take that hydronium, and the slightly negative oxygen in the ether can attack one of the slightly positive hydrogens in the acid. The electrons would snap back onto that oxygen to help stabilize its positive charge. So that there is this next proton transfer. Now that will leave us with basically the same molecule, but instead of a lone pair here, it'll be a bond to a hydrogen. And the oxygen will have a full positive charge because it has 3 bonds. That makes it an amazing leaving group. This oxygen here is a great leaving group because it has a positive charge. If it accepts electrons, it'll have a neutral charge. All it needs is a little push. And the carbon in between the oxygens is slightly positive because it's losing its electron density to both of them. So the electrons on this slightly negative oxygen next door have been eyeballing it. They try to form a pi bond to it, and that kicks this good leaving group off. So we have loss of a leaving group. So what we're left with here on the top is a double bond to this oxygen that has the hydrogen. And we also have this interesting diol. It's a dialcohol. So we have the OH with 1, 2, 3 carbons in between, and then the other OH. So that's this molecule here. Now, we almost have our ketone. We just have to do a proton transfer. And so we need to take that H+ off the molecule. So we bring in a water, can act as a base. The slightly negative oxygen in the water can steal the slightly positive hydrogen, and the electrons snap back onto the oxygen there. That's our proton transfer. And what we get at the end is acetone. So that simplest of ketones. The smallest ketone you could have. Here it's upside down. But remember, these are three-dimensional molecules. They can exist in any direction they want. So that's acetone. You might use it as nail polish remover. And that's ultimately the product that we get when we do this acetal hydrolysis. So to go through those steps one more time, to get from the acetal to the ketone, we wanted to kick the ether off, but it's a bad leaving group, so we did a proton transfer. That gave it a positive charge, and with just a small push, we kicked it off, loss of a leaving group. Once it was off, we had a good, strong electrophile, so we treated it with a weak nucleophile, water, and did a nucleophilic attack. The molecule we were left with was almost the hemiacetal. We just had to stabilize it by doing a proton transfer. Once we had the hemiacetal, we just need to remove the other ether. Right now it's a bad leaving group, so we did a proton transfer to turn it into a better leaving group. Once it was a good leaving group, we only needed a small push from the alcohol, and we kicked the leaving group off, loss of a leaving group. The molecule that we were left with was almost the ketone. We just had to stabilize the positive charge on it by doing a proton transfer, and we're left with the ketone. All right, let's do one more example of these, hydrolysis of acetals. So let's draw the acetal they give us. So there it is. Look for the carbon that has the two ethers on it. So we have one ether going here, one ether going there. You can see the carbon in the middle is going to be the carbon that has the ketone on it. So I'm just going to put a star there to help me keep track of this. Now, for the hemiacetal, one of the alcohols is going to come off, and one of them will stay. So let's say we keep this one on the right, the other one comes off. In the hemiacetal, in addition to that ether, we're going to have an alcohol. So one of the ethers we started with two, one of them stays on, the other one leaves and gets replaced by an OH-. The OH- is ultimately going to turn into the ketone. Notice when the other oxygen leaves, we're going to get a straight chain. The ring will be broken. And so our straight chain is going to have 1, 2, 3, 4, 5, 6, 7 carbons. So 1, 2, 3, 4, 5, 6, 7 carbons. Let me number those. On carbon number 3, we'll have the ketone. That's the ketone on carbon number 3, where the OH is. And on carbon number 7, we'll have the alcohol. Okay, so that's our general plan. We'll go from the acetal to the hemiacetal to the ketone. All right, let's start with the acetal. So we've got this here. And we want to get rid of one of those ethers, but they're both really bad leaving groups right now. So to make them better leaving groups, we can do a proton transfer. We're going to transfer a proton, an H+, from H3O+, the acid that they're giving us in this reaction. So let's kick this small ether off first. The slightly negative oxygen will steal the slightly positive hydrogen on the hydronium, and the electrons will snap back on to the oxygen in the hydronium to help to stabilize its negative charge. So that's a proton transfer. We're transferring a H+, a proton, from one molecule to another. And the product of that is going to be really very close to being that same thing. The only difference is that instead of this lone pair, we're going to have a bond there to a hydrogen. Now that oxygen has 3 bonds, so it has a full positive charge. And it's the positive charge that makes that such a good leaving group. Because if it has a positive charge on the molecule, then it can accept the electrons in the bond that are bonding it to the substrate, and that will stabilize that positive charge. All it needs is a little push. The carbon in between the oxygens has a slight positive charge because it's bonded to 2 oxygens that are stealing its electron density. The oxygen on the other side with a negative charge has been attracted to that slightly positive carbon this whole time. Well, now it tries to form a bond, a pi bond there. And because this is a good leaving group, it ends up kicking the other leaving group off, so we get loss of a leaving group. So now the molecule we have is this, that's what's left, and we also have a methanol. So notice we formed this second bond here. That gives this oxygen 3 bonds, so it has a positive charge, and the methanol left the molecule. Okay, well, this creates a really strong electrophile. The carbonyl carbon is really slightly positive. It's losing its electron density to the oxygen because it's bonded to it twice, but the oxygen has special powers. It has a full positive charge that it can use to pull electrons to itself even more. So the carbonyl carbon here is a very vulnerable electrophile. Now, we're adding water, and the water is going to be responsible for adding that OH onto the molecule. This is hydrolysis. We're breaking the acetal apart using water. So the water comes in and acts as a nucleophile. The slightly negative oxygen attacks the slightly positive carbonyl carbon and pushes the pi electrons onto the oxygen to help stabilize that positive charge. So that is our nucleophilic attack. The water attacks as a nucleophile. But what we're left with then is very similar to this molecule. Well, this now has 2 lone pairs, and so no charge. You still have the ethyl group there, but in the other direction we'll have the water. The oxygen has a positive charge because it has 3 bonds. Well, we're almost at the hemiacetal. All we have to do is stabilize that positive charge with a proton transfer. We can use another water molecule. The slightly negative oxygen will steal one of the slightly positive hydrogens, and its electrons will go to stabilize the positive charge on the oxygen. So we're transferring this proton there from one molecule to another. And that gives us the hemiacetal. So basically the same molecule here, but we won't have this hydrogen, and that bond will form a second lone pair. So we have the hemiacetal. There's a carbon that's bonded both to an ether and to an alcohol. Okay, the next step is to kick the other ether off. But right now the ether is a poor leaving group, because if it leaves you have a full negative charge on an oxygen atom. So to turn it into a better leaving group, we can do a proton transfer. We can combine the acetal with the hydronium that we formed in the last step, to this H3O+. The slightly negative oxygen here is attracted to the slightly positive hydrogens. And so it steals one. When it bumps against it in solution, the electrons go onto the oxygen to help stabilize that positive charge. So we're transferring this proton. This is a proton transfer. The product we get there is almost the same as the molecule we had to begin with. Oops. But now, instead of that lone pair, we'll have a bond to a hydrogen. That oxygen now has 3 bonds, and so a full positive charge. Well, now it's an amazing leaving group. This would be very stable if it just took electrons and popped off. So we can have loss of a leaving group. All it needs is a small push, and the push comes from the alcohol. This carbon in between the oxygens is slightly positive because it's losing its electron density to those 2 carbons. The oxygen in the alcohol is slightly negative, and so its electrons have been eyeing that slightly positive carbon. It tries to form a pi bond to it. Normally it gets pushed back, but this time there's a good leaving group, so the leaving group takes its electrons and leaves. We have loss of a leaving group. The molecule we're left with, we have the carbon now, with a double bond to the oxygen, with a single bond to hydrogen. The oxygen there has a full positive charge. That's this right here. We have an ethyl group on one side. There's our ethyl group. It's these 2 carbons. Now I've already drawn this carbon here. I'm going to draw 1, 2, 3, and then we have the OH on the other side. Okay, well we almost have our ketone. All we have to do is stabilize that positive charge by doing a proton transfer. So our last step is this proton transfer. We can take a water molecule, the water molecule, the slightly negative oxygen on it, can steal the slightly positive hydrogen here. The electrons snap back onto the oxygen, and we are left with our beautiful ketone. Now this looks a little strange, but if you wanted to draw it as a straight chain, we can number it 1, 2, 3, 4, 5, 6, 7, so we have 7 carbons. So 1, 2, 3, 4, 5, 6, 7, and we can number this. Off of carbon number 3, we have the ketone. Oops. And off of carbon number 7, we have an alcohol. And you'll notice that that is the same molecule that we drew originally at the very beginning here. Oops. We have the carbonyl off of carbon number 3, the OH off of carbon number 7. So we had this acetal. We did a proton transfer to turn one of the ethers into a good leaving group. Once it was a good leaving group, it gets kicked off by the other oxygen in the molecule, loss of leaving group. That created an amazing electrophile and water attacked in nucleophilic attack. We stabilize the water because once it attacks it has a positive charge, so we stabilize it by doing a proton transfer. Makes it neutral. We have the hemiacetal now. We want to kick off the other ether. We do it with a proton transfer. That turns a bad leaving group into a good leaving group. All it needs is a nudge from the OH, and you get loss of a leaving group. Finally, you almost have the ketone. You just have to stabilize that positive charge by doing a proton transfer. And you can rearrange the ketone that you get to draw it in a more conventional way. So hopefully this gives you some exercise, gives you some practice in seeing how you can apply the mechanism for the hydrolysis of acetals